So we're looking at properties of rational functions today, and more specifically, we're going to be exploring the horizontal and the oblique asymptotes a little bit more in depth. But we're not going to forget about our vertical asymptotes or the removable discontinuity. We're just going to add these into it. And we have our bottom-heavy situation when we have a degree that's bigger in the denominator than we have in the numerator. Then we have a horizontal asymptote at y equals 0. To the far right here, our top-heavy situation is if the numerator degree is bigger than the denominator degree, then we will have an oblique asymptote. And all that we had to do yesterday is we had to identify that we had an oblique asymptote. We're going to learn today more about how to write it in y equals mx plus b, also known as slope-intercept form. And our third situation here for identifying between the horizontal and the oblique asymptotes is if we have the same degree. And we look at the highest degree term on the numerator and the highest degree term on the denominator, and we take those coefficients to come up with y equals a over b for our horizontal asymptote. So let's look at an example here. And start far left on your paper, because I think that I left you enough space, but I just want to make sure that you have enough. And as we take a quick glance at this, what you might try to do, as I did, is try to factor out 2x squared minus 2x minus 1. But it just so happens in this problem that we cannot. We can't factor that numerator. So I won't spend the time on trying to factor it up here, but what we can tell here is if we look at this problem, typically what we would say is, well, what's the domain of this function? And we would take our x minus 1 and we would set it not equal to 0. And consequently, then we would add the 1 to both sides and we get x doesn't equal 1. And what we've learned earlier in this week is that vertical asymptotes go along with the domain. So if x doesn't equal 1, then our vertical is x equals 1. A couple other things that we can identify here. We couldn't factor the numerator, which means that we don't have anything to cancel out. And because we don't have anything to cancel out, we don't have any removable discontinuity. But when we get over here to the horizontal and oblique, what we're going to look at is we're going to look at our numerator. Well, our numerator has a highest degree. It's 2x squared. So we get degree of 2. Our denominator, our highest degree is x, which is degree of 1. And what we see from this is that this is a top-heavy rational equation. Well, if we go back up and we look at our chart, what happens in a top-heavy case, which is the farthest to the right on your paper, is that we have an oblique or a slant asymptote. And if we have an oblique, what that means down here is that we do not have a horizontal asymptote. And we want to come up with the oblique, and we also do want to draw the graph. So I'm going to write the function down again because I don't have enough space, but hopefully you have enough space. Our function was 2x squared minus 2x minus 1 divided by x minus 1. And what we have to do on this is we have to use synthetic division to divide. So different teachers set it up a little bit different way, but the underlying method is still the same. I personally like to write an upside down division bar. You want 2 spaces, like 2 lines of notebook paper in between them. And what we're going to do, the number in front of the x squared term is a 2. The number in front of the x is a negative 2 minus 1. Make sure that your function's in descending order. We have the highest degree term first, and then the next highest, and so forth. When we divide, down here, we have x minus 1. And what we're going to do is we're going to change the sign on the minus 1 and make it a 1. And finally, we're going to take the first term and we're going to carry it down. So once we have that set up, and again, some teachers write it like that and some write it a little bit different, but the underlying method is still the same. Now we're going to take 1 times 2, and we get 2. It's positive 1 times positive 2, which is positive 2. Negative 2 plus 2 is 0. 1 times 0 is 0. And negative 1 plus 0 is negative 1. Once again, what we're trying to do is we're using synthetic division now to come up with our oblique asymptote. What we started with is we started with an x squared term. We divided by a first degree term, and what happens is every time we divide, our degree goes down by 1. So what we're left with here is we're left with 2x plus 0 minus 1 over x minus 1. But in terms of the oblique asymptote, what we didn't talk about enough yesterday in our notes is that with an oblique asymptote, what happens is that as x approaches infinity or x approaches negative infinity, our graph is getting closer and closer and closer to infinity. But what happens is it follows a slanted line. So what happens here is we don't need to worry about the remainder. Chloe? I mean, that's what we divided by right here. So that's what the remainder is. But what we need to worry about is the rest of it. We're going to write our oblique asymptote in slope-intercept form. I just write y equals 2x. If you prefer to write the 2x plus 0, that's fine. Because then you've got your y-intercept and your slope. And now that we've got all that information, and maybe I went backwards. Maybe we should have graphed it first. We don't need to worry about that. And we type this into our calculator, we get this picture. And when we look at the table here, we can get a couple values to help us graph. Like negative 1 and negative 3 halves, which is negative 1 1/2. So negative 1 and negative 1 1/2 and 0, 1. And if we look at our picture again, it looks something like that, and I want to just modify that and tease it. Like this. One of the reasons that I knew to modify that is because earlier on we'd already done x equals 1. We have a vertical asymptote here. Our other branch, if we scroll through our calculator, and I don't have to, we have a value of 2, 3, and we have 3 11 halves, which is 3 5 1/2. So 2 3, 3, 5.5, and our picture looks not quite like that. And then the last thing is, because I'm not going to be able to draw it in as accurately, at least right this second, is if we come down here to y2 and we type in our oblique asymptote equation of y equals 2x. There's the oblique. It's a line that the graph gets closer and closer and closer to, but never quite touches. So I want to go back and redraw all this because my picture is not very good. Let's see if we can do a better job here. And what I'm going to do, first of all, is I'm going to put in the vertical asymptotes, and that'll probably help get the picture drawn. And one more thing. I'm really sorry, video people watching the video, but I need to orient this board. So let's put in the vertical asymptote. So there's the vertical asymptote, x equals 1. We can also put in the oblique asymptote of y equals 2x. We can start at 0, 0. And then we're going to go up 2 over 1, up 2 over 1, up 2 over 1, up 2 over 1, up 2 over 1. Or we can also go down to the left 1, down to the left 1, down to the left 1. So there's our oblique. And again, let's go back and look at the table one more time. And what we said in our table is that we've got a couple of good points. -1 and -3/2. So -1 and -3/2 is -1 and -1.5. And we also saw that value of 0, 1, a y-intercept over 0, up 1. So our graph follows there. Looks much better now. Let's look on the other side. And so I see a point at 2, 3, and 3, 11/2. 11/2 is 5.5. So if we go back to the graph, 2, 3, 2, 3, and 3, 5.5. 1, 2, 3, 4, 5.5. And there we get a picture.